Hello, everyone, and welcome back to the second half of day one, where we are going to have a special guest presentation. But first, it's day one. Like Dylan said, it's supposed to be a chill day, but hopefully you were able to get that spacecraft downloaded, access the learning platform. But how's it going? Tell us in the comments, how is day one going? Claire, how are
All
you
right.
feeling?
I am so excited to see their planets that they are working on. Make sure, guys, that when you figure out how to build your planet, that you upload a video, or not a video. If you want to do a video,
You
that'd
can
be
do a
great,
video.
but
Yeah.
a picture at least of you flying just over the surface so we can see your most alien planet and post it in the community under special awards so that you're eligible for that award for most alien planet on the last day.
That's right.
So, Natasha, we're getting some comments as we wait for the rest of those comments to come in. I have a riddle for you. Are you ready?
I'm ready.
So, Tusif said, how did Einstein begin a story?
Equals MC squared. I don't know.
That's relevant. Once upon a space time.
Oh, good one. I was like, where's the space connection? I like it.
There you go. All right, one more. Can you
Okay.
hang?
Oh, I got it.
Ready?
Okay.
Okay, from Olivia.
Hmm.
What happens when my friends send me into space without my suit on?
Not good things happen, Olivia. You do not want to go without your spacesuit.
Yeah, she said it makes my blood boil. Ooh,
Ooh,
yeah,
that is accurate.
accurate. I think she should get new friends.
We should ask Dr. Shamatov what happens.
I don't really want
Don't.
to think about it.
Yeah, true.
Okay, so it looks like we have some comments. We're building a solar system here. Oh, very cool. Awesome. A lot of people are having an amazing time. It's amazing.
That's that's a good way to spend day one. Just amazing.
Yes. All
All
right. I
right.
like that.
Well, keep.
Tusif laughed at his own joke. Way to
Oh,
go.
I was wondering what he was laughing at, but yeah, he's the one who submitted. So, what I would like to do is encourage everyone out there that is watching, please comment. And whenever we are bringing on our expert presenter here soon, we have questions that we got from you guys. So you submitted your presentations in that form. There's a few already in the community, but we will also use live questions. So for everyone watching this live, ask us all your questions. So as Dr. Shamatov is talking, please write in the chat, what do you want to know? And we will be able to ask those directly to a former NASA astronaut. So, oh, we have a comment. Did you see the last one?
I
Hey, if you want a
agree.
better space joke, you got to submit it. All right. Well, are we ready to start? So I can bring on Dr. Shamatov after I tell you a little bit about him. So, Dr. Shamatov served as a NASA astronaut for 15 years, including shuttle missions STS 124, 126, and 134, and space station long duration missions Expedition 17 and 18. He has lived and worked in space for almost 200 days as a flight engineer, science officer, and mission specialist. His last mission was on the final flight of Space Shuttle Endeavour, during which he performed 2 spacewalks, including the last one of the shuttle era, which also completed the assembly of the International Space Station. Dr. Shamatov has a bachelor's in electrical engineering from California Polytechnic State University, master's in aeronautics from Caltech, and a PhD in aeronautics and astronautics from MIT. He also has a minor and master's in planetary science. He's currently a professor of practice in aerospace engineering and director of the Aerospace Technology Research and Operations Astro Laboratory at Texas A&M, which performs research and development in space robotics, autonomous systems, and collaborative VR simulation environments, like we're doing right now. Dr. Shamatov is co-author and co-editor of Human Spaceflight Operations, a textbook on the lessons learned from the past 60 years of spaceflight. He was a space advisor on the Hollywood production of Ender's Game. He also co-created Zero Robotics with NASA and MIT, which is a worldwide space robotics programming competition at the middle and high school level. All right, let's bring him on.
But first, I want to share something that there was another joke that just came out, and I just have to share it. Why did Mickey Mouse go to outer space?
I don't know why. To search for something?
To find Pluto.
Hey, this name is familiar.
Is it? Who was
All
that?
right, this is perfect segue to Dr. Shamatov. Welcome to the broadcast.
Thank you. Hey, Dimitri. I think he's upstairs making fun of me or something, but that's great.
So
I
that
like
was
your
his
jokes.
pun.
I like all your jokes. I don't know what, I don't think you need new jokes.
Well,
Maybe
Claire,
we
you
can
want to show him
incorporate.
one more joke I see we just got from Astro Girl.
Astro Girl. Okay. Did you hear about the restaurant on the moon? Great food, but no atmosphere. That's a good one.
Those are good ones. We'll have to borrow them next time.
Well, Dr. Shamatov, they are very excited to hear from you, listen to your presentation. And at the end, as I mentioned previously, please submit your questions because when you're done, I know you would like to answer some of those student questions.
Yeah, sounds good. I'm all ready.
All right, if you're ready to go ahead and share your slides and I will bring them up. And we will be checking in with you. If you let us know if you need anything,
Yeah.
we'll be here in the background.
I want to make sure that you can hear me because I will be looking at my slides.
Well, we are bringing up the slides now and the stage is yours.
All right. Well, thank you very much for that introduction, and hope everybody's having a good time so far. It seems like it's going well for most people. My son, who's just publishing the new jokes here, made a beautiful planet that he's probably going to submit too. So watch out. He just started just like you guys. He hasn't done any, believe it or not, he's never done space teams until today, and so he's going right along with us. So let me go to the next page here. Yeah, I won't repeat that long and wonderful introduction you gave me, Natasha. But one thing to add, I think, is that I'm also adjunct professor at the University of Sydney, and we have a lot of folks from Australia here today, and from a lot of places all around the world today. So we're really excited that you're here. It's going to be a fun week. If you're still trying to get things working, then that's okay. We're here to help you. Just keep sending tickets to the help desk, and you'll also be able to go back and redo and make better everything that you do each day on the later days. So don't worry about finishing anything on any particular day. All right, so I'm going to talk to you just a little bit about space exploration and my missions and my experience a little bit. But I'm also trying to prepare you guys for tomorrow. Tomorrow is a big day because you got to design your ship. You got to design your spacecraft tomorrow. And you're going to have a lesson on that tomorrow and a tutorial on how to do it in spacecraft. And I'm going to tell you a little bit about also what you need to know about designing a spacecraft. Some of the technical stuff will be more in the lesson tomorrow, but we'll get into some of it tonight. All right, so as you know now, you're using this program called Spacecraft, and we use this to do real work for some NASA mission design, for things that are for companies that work for NASA to design missions and design hardware and test ways to train crew members and evaluate operations in different scenarios. Like right now, we're studying operational scenarios for the lunar surface, where crew members are inside the habitat and outside the habitat, and there's robots going around, and we're trying to figure out the best way to do things, and we're using spacecraft to do some of this work. So it's very exciting. And so you're using it for the particular mission that you're going through in over the next 6 days. And in the future, there'll be other possibilities that we can have competitions for all kinds of NASA goals that are coming up. Okay, so I just want to tell you a little bit about my own experience this is one of my favorite moments probably in my life. And you're kind of seeing two kind of related pictures here in a way. So I took this picture of the space station at a time we climbed right up on top of it. This was the very last spacewalk of the space shuttle program. So 30 years of spacewalks from the space shuttle. This was the very last one. I happened to be on it. I was very lucky for me and my crewmates. And we knew we were going to have this amazing view. And so we took a special camera lens out, and it's a very wide angle lens. So things are a little distorted. You can almost see the curvature, like this panel right here. That is not, that's obviously straight, but it doesn't look straight because of the wide angle lens. And so it makes things look shorter than they are. This right here from that's the shuttle. That's the nose of the shuttle right there. From here to here is a whole football field. And it's also a football field even longer than one, including the end zones, all the way across this truss. And so that solar panel is pretty far away. It's like the other end of a football field, and it's very big. What you're looking at right there is a full basketball court. That's the size, almost the same size and shape of a basketball court. So this is a huge thing, the space station that we've put up there. And then this picture is of me on the spacewalk, an earlier part of the spacewalk. Actually, I was right over here. We were doing something. You can see a little boom there. That's my hand is on it right there. And we were installing this boom, which normally would go up and down with the shuttle, and we were leaving it on the space station for long-term use after the shuttle program stopped. Anyway, this was an amazing moment. It was the last spacewalk to build the space station officially, and we got to announce that we completed this project after so many years and so many countries, 16 different countries, almost as many countries as are doing space teams today. Probably about the same, but not the same countries. But yeah, a huge project for a very long time, and an amazing thing to be part of. This was a pinnacle of human collaboration, across the world, and we all felt that way about it. It's very hard to watch what's going on now because relationships between Russia and all the other partners in the space station were terrific through this time. I spent half of about 10 years of my life in Russia, in Moscow and Star City, where the training is, and I have a lot of friends there. And so it's sad to see the breakdown, because of what's happening in the world today. Because we'd like to see this kind of cooperation, and this project, and others like it are, really important for bringing us together instead of, dividing us. Anyway, so this was kind of a pinnacle moment, but I'm going to kind of go backwards now. And so this is mission control, as you probably know, a very long time ago. That was me at the time of this picture, more or less, about 6 years old. And this was a really amazing time because the space program was just getting started. And I was, I was fascinated because also my father was fascinated with what was going on here. He really wished he could have a job like these people in mission control, and he wondered how they could even ever get such a job. Many years later, I got to be one of the flight controllers working in this room. And actually I sat right over here, and I see the person who's sitting right there was my crewmate, Mike Fink. I spent time on the space station with him. He's the Capcom right here in this picture. That's the capsule communicator, the person talking to the crew, and sitting right next to the flight director. And that also was a friend of mine, Ed Van Cise. And so I spent a lot of time sitting in that seat, talking to the crew, working in this room. So there's a huge history here, a huge trajectory that, always thought about this and dreamed of being part of it someday. So dreams can come true. And actually the time that this dream kind of started for me was the launch of Apollo 11. This was the first moon landing, and I happened to be in Florida on a family vacation, and I was exactly the age in the last picture, 6 years old, and almost 7, and got to see this launch, and sort of never turned back. I just, from that point on, this is what I always wanted to do. There's the picture of me I'm on the right, my brother's on the left, and then many years later, we were back in Florida again, and I'm on the right, my brother's on the left, and of course, I went back many times after that. So this is me probably about the age of, or close to the age of many of you. So this is probably senior year in high school. Pretty sure it is because the t-shirt was related to that. And I look a little different now, I guess. But so you guys are just a little bit younger than this. And then what happened is I went from there, started college. And this happened in my very first year of college, the shuttle launch for the very first time. And, and I'd been thinking about this my whole life. I had no idea what to do. And so I called NASA, and you can call them today, and you could speak, if you're interested in going to space someday, you can call NASA tomorrow. You can call the astronaut selection office at the Johnson Space Center. They'll answer the phone and they'll talk to you, and they'll tell you, they'll give you advice. And they gave me advice. And I followed it. That advice, you can ask me about that advice later if you want. How about that? And then what happened was, like, when I graduated from college, this person is Hoot Gibson, and he went to the same university that I did. It's the first time I met someone who flew in space. And all of a sudden I thought, wow, it's possible to follow in this person's footsteps, and could be true someday. So many years later, skipping way, way ahead, I was in this 17th group of astronauts. I'm in the back corner over here. And you're going to meet this one during the week, and you're also going to meet, let's see, you're going to meet a couple more. But anyway, we'll get to. As we go through a lot of training, the astronaut training is a lot of fun. Flying in space is awesome, but the training is awesome too. So this was survival training. This is also survival training, but water survival training. We fly over the ocean. We may have an emergency and land in the ocean, so we need water survival skills. This is practicing different gravity environments. So you may have heard of the Vomit Comet, an aircraft that flies up and does parabolas. And when it does that, you get the feeling of zero gravity for 25 seconds or so. And so we got to do that as part of our training. And then, if you have to bail out of the shuttle, the shuttle was actually designed, that you could jump out, if it couldn't land safely, you could jump out. And so we had a parachute, we had a lifeboat that was attached to us, and we had to be able to, parachute down to the ocean and get into our lifeboat, which is very small. It's this little thing that's just around us right here. So we practiced all this kind of thing. And then we got to fly regularly in the T-38s. And the reason for this, these are the NASA T-38s, it's a lot of fun. And especially for someone who didn't go to the military, getting to do this was amazing. But we do this because, as you can imagine, we can't go to space and train there. We have to train on Earth. And everything on Earth is a simulation of what it's like to be in space. However, flying these jets, it's a real situation. It's a real operation, and you have to think on your feet, make decisions, and the decisions have consequences. And so we use this because it's real time training in an operational environment that has real life consequences. So it's really important that we do those kind of things. We have other kinds of training we do for long duration flights. You can think of it as survival training, but it's really team building. And some of you probably have done some training like this, especially if you're in Scouts or some other program like that. We went out into northern Canada in the middle of the winter in February, which was the worst time to be there. And the temperature was -30 on average Celsius, but it doesn't matter whether you're talking Celsius or Fahrenheit. The two scales cross right about -30, so it doesn't matter which scale you're talking about. But it would go from -40 to -20. That was it. And we spent a week out there, and they were basically stressing us out, making us, get up in the middle of the night and take the camp down and move in the freezing cold to some other location and things like that, just to give us a lot of stress and make us lose sleep and be really cold and suffer and see how well we work as a team and really under really difficult conditions. You really get to know yourself and your crewmates when you're doing things like that. We do the same thing in Russia. This is a Soyuz capsule, Russian capsule simulated that landed off course, and we're in Siberia, and we have to survive until they can find us. And so that was a similar kind of exercise. And here also in Russia, the Black Sea, this capsule is actually supposed to land on land, not on the water. And And here we're practicing an emergency landing where we landed in the water, but there's some kind of fire or some problem with the capsule and we have to get out. We got to change out of these spacesuits into basically a waterproof suit, which is extremely difficult inside the capsule. But you do it and you get checked off and they let you go to space after that. We do a lot of training all over the world in different simulations. You know, as I mentioned, there were 16 countries involved in building the space station. And you can imagine every country has the highest fidelity simulation of its own stuff, its own components, its own models or parts of the space station. So this is the Soyuz capsule trainer. This is the part of the Russian part of the space station. We spent a lot of time there training, just as we did in the US and other places too, other countries in Europe and Canada, Japan. And of course, a lot of training underwater for spacewalking, which is, you know, the favorite part for a lot of us. And this is really a cool thing too. We did this, we do a lot of, we call spaceflight analog missions. Like what can we do on Earth that parallels in some way a space mission? And this habitat is off the Florida, off Key Largo in Florida. It's mounted on the bottom of the ocean. Of course, if you're living in there, you're totally dependent on the life support system, just like you are in space. You go outside using, you know, specialized gear to live outside in the water, right? So scuba gear, specialized gear though that we used, and we had a whole mission in here, and we conducted it just like a real space mission. Mission control back in Houston was actually involved. They're giving us all the commands of what to do. We're following procedures on our computers, written the same way as they are in space, and we even had a live link up with the space station from underwater, which was really cool. So a lot of training like this to give us an analog mission experience before going into space. The name here is Aquarius is the name of the habitat. NEMO was NASA Extreme Environment Mission Operations. Okay, so just quickly, some of the missions I was on. This was a shuttle flight bringing the Japanese science module to the space station. This is kind of a depiction of the science module with a Japanese flag on it. This is the most beautiful laboratory we have in space. Really amazing place. And I got to go up with it and then install it over the course of a 6-month mission. This crew came up. Aki here was a Japanese crew member. He's got a Japanese flag on his arm here. And so he got to help install it, but then he had to leave, and I got to be the first person to live with it for 6 months and take care of it and start the science program, which was an honor and also disappointing for Japan because I think they would have rather had a Japanese crew member do that. But anyway, I was part of Expedition 17, 2 Russian cosmonauts as my crewmates. And then we had a swap of crew on the Mike and Yuri came up. You were looking at the back of Mike's head in the control center a minute ago. They came up, they stayed with me for a while. I went down on another shuttle flight that brought Sandy up, and Sandy became part of the space station crew. I went down with this crew, and that's it. And then there was another mission I went on after that, which was a couple years later. And this was the one where I showed you the spacewalk and the picture that I showed you at the beginning. This was the last spacewalks to build the space station. And we also installed something called an alpha magnetic spectrometer, which is a giant cosmic ray detector that's still up there doing amazing science, looking for antimatter. And we installed that on the space station. And this is one of the folks you're going to meet this week. We call him Box. His name is Gregory Johnson. He calls me Taz, and I call him Box. So, all right. So I'm going to show you a quick video of what it's like during a mission. And then on the other side of that, we'll keep going. So let me know if you hear the sound. It'll take about 3 seconds for it to start, and then we'll keep going.
this final flight of Space Shuttle Endeavour. We want to thank all the tens of thousands of dedicated employees that have put their hands on this incredible ship and dedicated their lives to the Space Shuttle program. As Americans, we endeavor to build a better life than generations before, and we endeavor to be a united nation. In these efforts, we are often tested. This mission represents the power of teamwork, commitment, and exploration. It is in the DNA of our great country to reach for the stars and explore. We must not stop. To all of the millions watching today, including our spouses, children, family, and friends, we thank you for your support.
It's a final countdown.
Okay, home's burn starting in 5 seconds. Now. Here we go. Whoa!
Spectacular ride. I couldn't see anything but the lockers, but it was still a lot of fun.
No master alarms.
I'll have to say it was a lot different than flying on the Soyuz.
We've so many light years to go, and things will be
You're upside down.
Hey, didn't I see you up here last time? You were upside down last time too.
You're still upside down.
Oh, you're upside down.
It's a final countdown. The final countdown. The final countdown.
All right.
You guys look great. You know why I'm wearing these? Because it looks cool.
Hey, I've got a pair of those. Yeah. Hey, I want that experience.
Some Fiesta chicken. It's the best stuff.
In Houston on the big loop, we're tally ho with the station. Initiating RPM on my mark. 3, 2, 1, mark. Houston and station capture is confirmed.
Endeavor arrived.
Dima! Welcome to the station.
Daring us to dream of places far away inside. Your light inspires all, unleashing the soul's desire. Our world eternal love, the changing faces that you wear, reflecting back to all.
For the OPS standoff, use a very ultralight ninja graceful ballerina grip, as we talked about. EV2 is ready with ninja ballerina grip. In behalf of the STS-134 crew and the Expedition 27 crew, Space space station assembly is complete.
This space station is a pinnacle of human achievement and international cooperation. And now it's the brightest star in the sky and hopefully the doorstep to our future.
Okay, can you hear me still?
Yes, we can hear you.
Okay, good. I'm glad. I hope that you enjoyed that.
That was awesome.
All right, cool. We want to use the rest of the time here to talk about how to build a spaceship. And here's some books on the subject. And I don't recommend the one in the middle, Zombie Spaceship Wasteland. That one isn't very helpful. I didn't actually read it. I have read one of these books. I've read this one, How to Build Your Own Spaceship. It's not exactly what you think it is in this book, but it is a good book. This was probably a good one. But anyway, there are actual manuals and there are actual books that you can read to learn more about this. One of them happens to be the one that Natasha mentioned at the beginning that I was part of putting together. You can look for that one. That's not really about designing spaceships, but it's all about them, all about operating them. So building them is difficult, and these all seem to be the wrong size, and for one reason or another, not probably successful designs, but certainly fun ones. I have to admit, I built something like this when I was younger. Tried to build a flying saucer that really flew and tried to fly it around the neighborhood and scare people, but it didn't work out so well. There's a bunch of key systems that you need to have on your spacecraft. So I kind of want to run through these with you quickly. So first there's, the exterior design and the interior design and then, why you need it to be a certain way. I'll just mention the topics here because we're going to get into each one. Propulsion, right? Your rocket engine, power systems, electricity, life support. How do you know where you are? How do you make the ship go where it needs to go? It's guidance, navigation, and control. Communications, command and data handling. This is like sending commands to the spacecraft and also sending data to where it needs to go, sending it back to Earth or wherever. Controlling the temperature of the spacecraft. Taking care of the crew. Robots and robotics to help you manage all the systems and things that are hard to do for humans or dangerous maybe. EVA is extravehicular activity. That's spacewalking. And okay, so we're going to start at the first one, exterior design. And there's a lot of really cool spaceship designs here. And I don't know about you guys. Some of you are probably like me, and I can name most of these, or a lot, oh, not really most of them, a lot of them. I can name a lot of these from the different science fiction movies over the years. If you blank the names on them, I could probably do a pretty good job of naming them. But these are huge. These are huge designs, and you don't have a sense of it really until you look up here. This is the space station, the huge space station. I just told you it's bigger than a football field. It would take 2 football fields to sit it down on the ground. That's the space station. These designs are, a lot of them are a lot bigger. But you could do this in space, just like a big ship in the ocean can be really, huge. In space, if the ship's going to stay in space and not enter the atmosphere of a planet, it can be really, really big. It's possible to build things like this one day. We don't know about their propulsion systems and being able to do what they do, but a lot of these, I expect the cool idea to me is that someday we're going to see some of these designs actually built just because we can build something that was envisioned from so long ago. And then there's the really big ones like Battlestar Galactica and Star Wars ships and Excelsior and a bunch of things here. Okay, this is my favorite one, and I don't know if you remember this one, but hopefully you've seen it. The cruise ship in space from Wall-E. That's the best one. All right, so what are the considerations for the design, for this exterior design? Get to the pictures in a second. What is this ship for? Is it going to be in space? Does it have to go into an atmosphere? Does it land on a surface of something? That's going to make a big difference as to whether, what shape it can be. You can't have something that looks like this and have it land on the surface or fly through an atmosphere, for example. So the shape also, if it's going to fly through an atmosphere, it might want to have wings. If it's something that uses solar power and those panels have to stick out, or that could be a factor if you're trying to dip it into an atmosphere to use the drag to slow yourself down when you're arriving at a planet, for example. Similarly, the materials you build it out of depend on the stresses you're planning to put it through. If it's, depending what it has to do and what it has to support. But the materials also are for protecting you from radiation and things like that. So there's a lot of considerations, and that's the next point here actually. So MOD is micrometeoroid orbital debris. It could be made by us from parts that have fallen off of spacecrafts and rockets, or it could be just asteroids, right, that are still flying around everywhere, and the radiation from the sun and also from deep space. You need to figure out what kind of instruments you're going to have on there, sensors, antennas, your thrusters, how you're going to control this thing and make it do what you want. You're going to want windows if there's people on board, and then you got to figure out how you're going to power this thing. Can you use the sun? Is it too far away from the sun to get enough power from the sun? You need to use nuclear power or some other fuel source. And then one of the things we don't have on the space station is gravity. Artificial gravity. But if you spin something, you could get artificial gravity. These are all things that spin in these pictures. So this was an original design that basically had these, the whole thing would spin, and you'd have artificial gravity on the inside of the outer ring here that you see. So if you spin it fast enough, it could be the same as gravity on Earth. This is a much bigger one. And this one is a smaller one where you have, two modules that are separated by a truss, and you're living in one. You may have storage in the other, or fuel and things like that. And the whole thing rotates and gives you gravity, on one side. So there's various possibilities for this. All right, what about the interior design? And you guys are going to be doing this tomorrow. You're going to be putting these kind of racks inside your spacecraft. The one behind me right here is a glove box for doing research. That whole thing actually slides out. You can put experiments in there, and you're protecting the crew and the atmosphere from the experiment, but you might also be protecting the experiment from the crew. So those holes are gloves. You reach your hand in there, then your hands are in gloves, and you can work with the experiment in there, and there's a barrier. This probably looks like a total mess to you, like all these wires everywhere. Why is that a good interior design? It actually is. There's a reason for this. Maybe we can do a lot better in the future. I'm sure there's other ways. But the reason for the mess, the wires everywhere, is that you see what this rack looks like on my back here? All the racks, everything in the wall looks like that. It's a big, giant fridge-sized rack. And when they're all installed, if all the connections were not nicely hidden behind them, if you had to undo something or change something or pull out a wire or connect something, you'd have to pull the whole rack out of the wall, get behind it somehow, and do the wiring. So to speed things up and to make it easier, all of our connections are on the front. And we have in these, we call them standoffs. It's down in the right corner here, in the corners, like right there, right there. This is like a cover right here for the standoff area, these corners, because you're in a cylindrical module with the square, living space down the middle. So all these racks have curved backs, and they can rotate out into the kind of the hallway. And in those corners, we have all the connectors for power, for data, for gases, for oxygen, for carbon dioxide, for accessing the vacuum, for sending data, video, to and from all these experiments and everything. And we connect them from those racks right to the front, and that makes it really convenient. So it's a mess, but it works. And so you have to think about these things, when you're trying to design the inside of your spacecraft. Where should things be? How do you make sure you have access to the tools? You don't want the crew wasting time, looking for things. You also don't want them bumping into each other because you put two things near each other that are inconvenient. Anyway, look at this picture. I want you to look at this picture at the bottom right corner because I think it's kind of fun. Sergey here was the commander, and he's making me do all the work, right? I'm carrying all the heavy stuff around. Actually, if you think about it, like how did we get this picture? Well, we were moving that rack from one place to another and installing it somewhere else. What we did was we let go of it. We let it float there. He got out of the way. I climbed underneath it, and I pretended I had it on my back, And then I got out of there and we kept moving it. It just floated right there for that picture. So it's a different environment being in zero gravity. Okay, so we have to keep our crew alive. We have to have life support for the crew. Very important function if it's not a robotic vehicle. Just to give you a sense of what it would take to keep a person alive by sending everything they need. We need food, we need water, we need oxygen. If we send it all from Earth, it's about 26,500 pounds or about 12,000 kilos for 1 year at the cost of about $100 million to keep one person alive for a year in space. And I think that number has gone up since I found that number. So it's huge cost if you try to bring everything up. So we can't do that. We have to recycle. We have to recycle everything we possibly can. And so that's what we do. And this is the system that we have on board. And I'm going to try to give you like a really short explanation of it. But basically, we want to have the right amount of oxygen, right, and nitrogen in the atmosphere. So we make it, right? Nitrogen, we breathe it in and we breathe it out. So we don't have to make it. We can just keep a tank of extra nitrogen and we're good. The oxygen, we have to make it. We make it from water. You guys know water is H2O. It's got oxygen in it. We electrolyze it. We make the oxygen. Hydrogen, though, is dangerous to keep around. So we were venting it overboard for a long time. We'll get back to that in a second. We control the temperature and the humidity of the atmosphere. We basically bring it into a machine that absorbs the humidity and captures that water. Then we recycle that water. This water is nasty, actually, when you try to clean out the pipes, because it's sweat and stuff like that that's evaporated into the air or whatever, and then it's collected, and then it's nasty. But it gets recycled. A lot of the water gets recycled. We process it, and then for the air, we want to get the carbon dioxide out of the air because we're breathing out carbon dioxide. That's actually toxic pretty quickly if the level gets too high. So we have to take it out. So we have machines to do that. I'll show you one in a second. And we were just venting that overboard. So we were losing carbon dioxide and losing hydrogen. When I lived on board, that's what we were doing. But since then, and the second time I was up there, we installed a system that combines this carbon dioxide with the hydrogen. It makes methane and water. And methane we could use as rocket fuel if we wanted to. We're not doing that on the space station, but on Mars we would. We'd use it for rocket fuel. And it makes water. It makes a ton of water. And so we take that water and we put it back into our water processing system. And that's how we recycle everything on the space station. All right, so a couple just quick pictures. Here's a picture of us basically drinking this is yesterday's coffee, but basically it means somebody drank something, peed it out, recycled in this urine processor, and then is ready to drink it again the next day, which is kind of strange, but it's actually cleaner than the tap water you have in your house. So it's not bad. So we have tons of equipment on board for taking care of the atmosphere for us. We got to generate oxygen, and we need backup systems, right? Because if a system fails, we have to breathe while we're fixing it, right? So we have extra oxygen tanks. We have other ways to make oxygen. We have a lot of systems that can back up each other. We analyze the gases on board to make sure that they're safe to breathe, and what do we have to do to clean the gas? If something burns or catches on fire, or something off gases, which materials do, they put chemicals out into the atmosphere. We have to be able to breathe the air, so we analyze it and we can also filter it. And this is about the carbon dioxide, getting the carbon dioxide out of the atmosphere. This is what a carbon dioxide scrubber looks like. Imagine somebody gives you this picture and tells you, go fix it. That's what happened to me. Wasn't quite as bad as that, but it was an 8.5-hour job to take this thing all the way apart and put it all the way back together again. All right, so that's life support systems, power systems. We had various ways to do this. On the space shuttle, we had these things called fuel cells. This was a really neat idea, and it worked out really well with the space station too, in that so we have big hydrogen tanks and big oxygen tanks. Hydrogen and oxygen together is a very powerful reaction, gives you a ton of electricity. So the space shuttle, that's how it got its electricity, but it makes water. Hydrogen and oxygen together make water. You get a ton of water out of it and a ton of electricity out of it. And so when the space shuttle was up attached to the space station, we'd make the water and we'd make the electricity, And even though the water was a byproduct and we got much more than the shuttle needed, space station needed water. So we would ship this water over to so the shuttle didn't really need to bring water up. It just made the water when it was there. It was a nice combination. We use solar panels on the space station, these massive solar panels we talked about. And here's another example, a nuclear device. It's called a radioisotope thermoelectric generator. It's used on a lot of deep space robotic missions. It generates a small amount of electricity, but for a very, very long time. So you're going to hear in a couple of days about some of these robotic missions like Voyager that have left the solar system and have been going for 50 years. And they're still going on this kind of a system, this kind of a power system. It's amazing. But for the future, we've been working on this, or NASA's been working on this. It's called CRUSTY. It's a nuclear power fission generator. And this is a nice big picture of it, but here's what it looks like. If this was like a rover for 2 or 4 people, you can fold it up on the back like that. So give you a sense of the size. It's not that big. It's actually portable. And this will give you 10 kilowatts, which is enough power for your house a lot of the time. The advantage of this is you can get this power anywhere. So if you're really far away from the sun, I mean, Mars is farther away, but if you're way further, like if you're on a moon of Jupiter and you need power, sun is really far away. You're not going to get much solar power from it. You're going to have to do something like this. All right, let me see, check the time here. Okay, so I'm going to go speed up. I'm going to skip just a couple of slides here to make sure I don't take too long. So for propulsion, we're going to have some kind of rocket engine or something that's going to push us, forward. And this is Newton's law. For those of you who know Newton's laws, I'm sure all of you have heard about it. But actually, equal and opposite action reaction. You push stuff out the back, you're going to go the other way. How fast are you going to go, or how fast can you speed up? How much you're going to accelerate, change your velocity? Depends on the amount of force and how heavy you are, your mass, right? But that's what we basically do. And there's a picture of my kids a long time ago at for those of you in Sydney, that's in the Wax Museum in Darling Harbor. So my kids with a wax figure of Einstein there. But so there's this thing called the rocket equation, and many of you guys certainly have the math to understand this. Some of you do not. If you know what a log function is, you do, and some of you in high school are very familiar with that. But I'm going to tell you what this equation means, in words. Basically, how much you can change your speed. That delta V, that means how much you're going to change your speed. How much you can change your speed depends on basically the mass of your spacecraft. How much of it is fuel? And then how efficient is your fuel? How powerful is your fuel? That's this ISP. That's how powerful your fuel is. G is just gravity. And these numbers don't mean anything to you immediately, but I'll explain what they mean. So with the best rockets we have, we can get changes in speed of about 10 kilometers a second. If our ship is 90% fuel. Can you imagine making a spacecraft where 90% of it is all fuel? It's not very good. There's not a lot of room to have, crew quarters and, other things on the ship if it's 90% fuel. But you would need it to be 90% fuel in order to get this much change in speed. How much is that? Is that good or bad? I'll tell you in a second. To get 20 kilometers per second change in speed, you'd need 99% of your ship to be fuel. So that doesn't make any sense, right? But this is what you need to get around the solar system. So now you'll understand the number a little bit. You need 11.2 kilometers a second to get away from Earth. So you need a ship that's 90% fueled to get away from Earth with the engines we have, with the chemical engines that we have. If you want to get away from the whole solar system, you need 42 kilometers a second. To go to visiting a bunch of planets, like in the future, if you were to go to Mars and then go somewhere else and then come back, just to kind of travel around our solar system, we need these kind of numbers. And to go to the nearest star, you need 120,000, like totally crazy number compared to 10. So it's really hard to get around because our fuel, that's the maximum capability of our fuels. And our best fuel is hydrogen and oxygen. That is actually our best fuel. And this is how good it is. This is just, doesn't matter what the number means exactly, but it's a number that measures how good the fuel is. And hydrogen and oxygen, it gives you this number, 453. We do have better ways to do it. You've probably heard of ion engines. We can get 30,000 efficiency from an ion engine. It's way better than this, right? But the problem is it doesn't push very hard. It's really efficient. In other words, the amount of fuel you have to carry, you can get a lot of speed out of it, but it takes a long, long time. It doesn't push very hard. Not hard enough to get off the ground, for example. You can only use this in space, and it would have to wait a really long time. So you wouldn't want to be on a ship powered, a human wouldn't want to be on a ship using an engine like this. It takes too long to get anywhere. Fusion is what we really need, nuclear fusion, which we don't have yet as an engine. And then you've heard of antimatter. That's amazing. Look at that. If it's compared 453, the best we can do now with 10 million, obviously that's amazing. But even this, if you want to go to the nearest star and you want to get there in a reasonable amount of time, like a lifetime, you would need 95% of your ship to be antimatter in order to do that. So even with antimatter, it's still really difficult to get around or to get far from our own solar system. Okay, so we use a few tricks to do this. We drop things off that are no longer needed, that are carrying fuel, makes the rest of it lighter, and we can push it further. That makes it possible for us to go to the planets, at least for the missions that you've seen, without having to carry 90% fuel. That's how we do it. Another thing we do something called a gravity assist. We fly by a planet and use its gravity to pull us. It changes our direction, but it also speeds us up. And you'll hear more about that in the talk in a couple of nights. Here's a picture of a spacecraft doing a bunch of flybys of Earth and then Mars and then Earth again. And each time it flies by a planet, it uses the planet's gravity to pull it along and then sling it further out. So that's these are some of the tricks that we can use to help us. All right, so I'm going to go through a few of the other systems here, and then we can take your questions. So we need communication systems. This is like magic, you don't realize it because we all have our phones and we talk to everybody with no wires attached. It's like a magic little box where your friend is in the box. How does all that work? It is amazing. We couldn't do spaceflight without it. Something is really far away in space and we need to send commands and get data. We wouldn't be able to do anything with a spacecraft unless we could get the data back from it. So it's really amazing that we have this. And we have all kinds of networks. I'm not going to explain the details, but we have satellites that we send signals to from the space station or other spacecraft, and those go down to the ground. And we have other radio frequencies we can use to talk locally, like between the space station and a crew member or the shuttle, things like that. And now we're developing them for the lunar surface. We know how to do this stuff, and we're starting to get into laser communication, which is going to give us a lot more data, possibly a lot more video capability, even from the moon, for example. We have to know where we are. Like when you're in space, how do you know where you are and where to go, which way to go, how fast to go? That's what this subject is, and we have to have obviously thrusters, but also things like GPS. These are actually gyros, but we also have these are GPS satellites. So we have the ability to figure out where we are and also push the vehicle in exactly to be where we want it to be. The spacesuits, is something you have to have on a human mission to repair things, to install things. I mean, if we're on the moon, we're going to be doing these spacewalks all the time, or moonwalks all the time, every day. And these spacesuits are amazing. And I was just in a meeting the other day to hear all about the newest spacesuits. And this is for floating around the space station in zero gravity. It's not for walking on the moon, but the new ones are made. They're similar in some ways and better in many, and allows you to walk and have flexibility, and you can bend over, pick things up, and be outside longer and things like that. But it's an entire spacecraft in itself. It's got to have life support. It's got to have thermal control. It's got to have cooling, and it's got to have all the things that a whole spaceship has, all in one little package to protect you. So pretty amazing things. Quick pictures about spacewalking. That's one I showed you earlier. Here's me coming out of the hatch, and here's a fun picture. So this is out on the truss. So I was telling you how big the space station is, but here you can really get a sense of the size. I think you can find one crew member right here. That's my crewmate Drew. I don't know if you can see another crew member. I'll give you 3 seconds to try to find another crew member in this picture. There, that's me on the truss. These are, and we're just seeing one little part, like this solar array. You're seeing one little part of it. So like this part right here isn't even, not even, this is like half the basketball court, you know, right here. All right, so we have a ton of robots to do a lot of work outside. If you don't want to have to do a spacewalk, if you can do it something with a robot, we have robots that can help us inside to do tasks and help us with procedures and things like that. This is what Natasha mentioned when she introduced me. This was these robots, we have competitions with them, and students can program them and fly them on the space station. It's called Zero Robotics, and it's a really fun competition that I'm also involved in. Got to take care of the humans, and there's all kinds of problems with being in space, and you've probably heard of some of these things: bone loss and muscle loss and problems with your heart, and all this stuff is true. And it can affect our performance and how long we can be in space, especially if it's not in full gravity. So we have to do a lot of operations on board, to study and take care of the crew, and especially when we go further, like to the moon and Mars, we need much more equipment because we can't just jump in a spacecraft and land in a couple of hours like we can from the space station. All right, and then there's a couple of things I'm not going to talk much about. You can ask me about them. The food, we have to, we have to provide the food for the crew, and that's really come a long ways. The food in space is great, but we certainly miss some things on the ground. We got to take care of ourselves in this environment, do a lot of exercise, especially because of the low gravity. Your heart's not working very hard during most of the day. We have to sleep, and we have sleep stations that we can live in and have a sleeping bag and a computer and some private stuff like your books or your journal or whatever. And got to take care of yourself in space. And it's kind of like a camping trip. If you've ever been camping, you know that doing your hygiene in the woods on the mountain is different than doing it at home. And it's kind of like that way in space. You're going to have to learn a different way to do everything, because we don't have a shower. This is the shower. You're looking at it. Karen here is washing her hair in the shower right now. That's it. Okay, well, that's it. That's what I wanted to show you guys for today. I hope that was interesting to you. And I guess I can switch back to talk to you guys face to face and answer any questions you have.
All right. Do you see us again?
Yep.
Great. Well, the questions were rolling in. So you had a captive audience of students, and you did say, here's a question you can ask me. And I'm going to start with that one, which was you picked up the phone and asked for advice. And so Ethan wants to know, what advice did you get?
Okay. Yeah. So, the astronaut office doesn't want people to spend their whole life aiming for doing exactly that. They want people to do things that they love to do and would do anyway. And so their advice was basically, whatever you do it with passion. Give it your all. And don't do something just because you think somebody wants to see it on your resume. Do it because you love it, because you're really interested in it, because those are the kind of things you're going to do really well at. And so that was the main advice, which wasn't a long list of extremely helpful advice, right? But it was important advice, and I think it's good to think that way, that you got to do things for yourself and follow your own dreams and passions. So those are good words.
That's really helpful. Well, here is another question that we got in the comments. What was the biggest challenge you faced while going into space?
Well, you said going into space, and that makes me immediately think about the right answer, which was, it wasn't when I was in space. It wasn't what I did up there. It was the going. And it wasn't the preparation for going either. It was the actual going, because when you're going into space, you're leaving your family behind. And that was the hardest thing to do. My kids were very young the first time I went. I was going to be gone for 6 months, and they barely understood what was going on. saying goodbye to them, and not being sure 100%, like I'm supposed to come back, but some people haven't, and you just don't know. So saying goodbye was the hardest thing, and after that, I loved every minute of being in space, and I also loved coming back to my family.
Mhm. I'm going to ask you one more that is a pretty kind of deep question. What did you learn about yourself and about our planet in your time in space? Emily from Australia.
Yeah, well, that's a good question, isn't it? Yeah, I keep going back to, you know, um, this idea of us all being part. I mean, I know people have heard this, that this overview effect, that you get to see the world as a whole, and but the thing that really struck me was, you look at the Earth out the window and the picture behind me, even though I wish it was real, but it's just a picture of the real thing. When you look at that, you know that you're part of it. You know that even though you're separated from it, and maybe you could even go further away. I'd love to go much further away and look back and see it as a dot in the sky. But no matter how far away I got from the Earth, I would know that I'm still a part of it. It's like a mother, just like my actual mother. Um, and but the cool thing about it is that the Earth is not aware of itself. It's a giant rock, floating in space, and all this life on it is aware of itself. It does have self-awareness, and so we're very special. Even though we're really small compared to the size of the Earth, we're the part of the Earth that can look back at itself and appreciate it for what it is. And so it's kind of an honor to have that role, to be the part of the Earth that can appreciate itself. And that's true for all of us. We all should feel that way. You don't have to be in space to feel that way.
Yeah. And so now, as you know, there's students from around the world that are part of space teams. Is there any message you want to give out to these students who are trying to figure out spacecraft, just getting started? We have a whole week of activities. What would you like to tell the students?
Well, I like what you said at the very beginning today. And you said, just relax, just chill. It's okay.
That was Dylan.
Oh, yeah, okay. Because so yeah, you guys are going to be masters at all of this by tomorrow. And today it's probably a little overwhelming. But the website, once you look at everything on the website, then you know everything that's there, and you'll be chatting to each other, and you've already downloaded the software. Once you've got it working, it's working, and and once you've figured out how to go watch the lessons and the tutorials, the next ones are in the same place, and you just go do the next day, and then the challenge will be the actual mission, right? And that's what we want. We want your challenge to be the space mission, figuring it out, designing the mission, trying to make it the best mission possible, and and ultimately what you're trying to do here, as you already know, is carry out this mission to go to this planet that's passing through our solar system called Vulcan, and then you want to be able to live on it as long as possible. You want to be able to sustain human life there, and so figuring out how to get everything there and use it in the best way for sustainability, which is also a really important thing for us to do on Earth. That's a good challenge, and you have the week to figure it out. And you'll be able to go backwards, and you will go backwards to the ship you build tomorrow. You're probably going to go back later and make it better, because you're going to understand what you're going to need to do to make it better in order to live longer on the planet that you're visiting. So it's going to be a lot of fun. I just say, enjoy, learn as much as you can, and work together as a team. Like, the whole point of this is to realize that you can accomplish so much more as a team, thinking about things, and and this package gives you the opportunity to collaborate together online. So so take advantage of working on a team, and the teamwork to solve the problems and figure out how to get from here to there, and maximize your score and see where you come out. But I hope you'll have a good time and learn a lot, and good luck.
Awesome. Well, thank you very much, Dr. Shamatov, for sharing your story and all the great information. I have provided a link in the comments for students to continue asking you questions in the community. So if they have more questions, I know you were going to go in and address some of those. So I appreciate that. So if you guys have any more questions, go ahead into that community. And now is your chance to go back into spacecraft, go back and finish the lessons wherever you left off. We'll be out here for a little bit and we'll come back tomorrow to kick off day 2. So best of luck. And as Dr. Shamatov said, work as a team. You're in this together. So help each other out and reach out to space teams if you need any support. All right. Good luck, everyone. We'll see you in day 2.